maybe inspiration for, or one of those would be remembered as the early steps of a new age of space exploration.
Yeah, I mean, during the launches itself. So I mean, the thing I think maybe some people know, but a lot of people don't know is like I'm actually the chief engineer of SpaceX. So um, the I've signed off on pretty much all the design decisions, and so if there's something that goes wrong with that vehicle, it's fundamentally my fault. Um, so I'm really just thinking about all the things that so when I see the rocket, I see all the things that could go wrong and the things that could be better, and the same with the Dragon spacecraft. It's like other people will say, oh, this is a spacecraft or a rocket, and this looks really cool. I'm like, I've like a readout of like, these are the risks, these are the problems. That's what I see. Like, so it's not what other people see when they see the product,
So let me ask you then to analyze Starship in that same way. I know you'll talk about in more detail about Starship in the near future, perhaps.
We can talk about it now if you want.
But just in that same way, like you said, when you see a rocket, you see a sort of a list of risks. In that same way, you said that Starship is a really hard problem. So there's many ways I can ask this, but if you magically could solve one problem perfectly, one engineering problem perfectly, which one would it be?
On Starship?
On Starship. So is it maybe related to the efficiency, the engine, the weight of the different components, the complexity of various things, maybe the controls of the crazy thing has to do to land?
No, it's actually by far the biggest thing absorbing my time is engine production. Not the design of the engine. I've often said prototypes are easy, production is hard. So we have the most advanced rocket engine that's ever been designed. Because I say currently the best rocket engine ever is probably the RD-180 or RD-170. That's the Russian engine basically. And still, I think an engine should only count if it's gotten something to orbit. So our engine has not gotten anything to orbit yet, but it's the first engine that's actually better than the Russian RD engines, which were amazing design.
So you're talking about Raptor engine. What makes it amazing? What are the different aspects of it that make it like? What are you the most excited about if the whole thing works in terms of efficiency, all those kinds of things?
Well, the Raptor is a full flow staged combustion engine, and it's at operating at a very high chamber pressure. So one of the key figures of merit, or perhaps the key figure of merit, is what is the chamber pressure at which the rocket engine can operate? That's the combustion chamber pressure. So Raptor is designed to operate at 300 bar, possibly maybe higher. That's 300 atmospheres. So the record right now for operational engine is the RD engine that I mentioned, the Russian RD, which is, I believe, around 267 bar. And the difficulty of the chamber pressure increases on a nonlinear basis. So 10% more chamber pressure is more like 50% more difficult. But that chamber pressure is that is what allows you to get a very high power density for the engine. So enabling a very high thrust to weight ratio and a very high specific impulse. So specific impulse is like a measure of the efficiency of a rocket engine. Or it's really the exhaust, the effective exhaust velocity of the gas coming out of the engine. So with a very high chamber pressure, you can have a compact engine that nonetheless has a high expansion ratio, which is the ratio between the exit nozzle and the throat. So engine's got like you see a rocket engine's got like sort of like a hourglass shape. It's like a chamber, and then it necks down, and then there's a nozzle, and the ratio of the exit diameter to the throat is expansion ratio.
So why is it such a hard engine to manufacture at scale?
It's very complex.
So what does complexity mean here? There's a lot of components involved.
There's a lot of components and a lot of unique materials that so we had to invent several alloys that don't exist in order to make this engine work.
So it's a materials problem too.
It's a materials problem, and in a staged combustion, a full flow staged combustion, there are many feedback loops in the system. So you basically you've got propellant and hot gas flowing simultaneously to so many different places on the engine, and they all have a recursive effect on each other. So you change one thing here, it has a recursive effect here. It changes something over there, and it's quite hard to control. There's a reason no one's made this before. But and the reason we're doing a staged combustion full flow is because it has the highest theoretical possible efficiency. So, in order to make a fully reusable rocket, which that's really the holy grail of orbital rocketry, you have to have everything's got to be the best. It's got to be the best engine, the best airframe, the best heat shield, extremely light avionics, very clever control mechanisms. You've got to shed mass in any possible way that you can. For example, instead of putting landing legs on the booster and ship, we are going to catch them with a tower to save the weight of the landing legs. So that's we're talking about catching the largest flying object ever made on a giant tower with chopstick arms. It's like Karate Kid with the fly, but much bigger.
Pulling something like
that. This
probably
won't work the first time. Anyway, so this is bananas. This is banana stuff.
So you mentioned that you doubt, well, not you doubt, but there's days or moments when you doubt that this is even possible. It's so difficult.
The possible part is, well, at this point, I think we will get Starship to work. There's a question of timing. How long will it take us to do this? How long will it take us to actually achieve full and rapid reusability? Because it will take probably many launches before we're able to have full and rapid reusability. But I can say that the physics pencils out. We're not at this point. I'd say we're confident that let's say I'm very confident success is in the set of all possible outcomes.
Right. It's not an all set.
For a while there, I was not convinced that success was in the set of possible outcomes, which is very important, actually. But so we were.
So you're saying there's a chance.
I'm saying there's a chance, exactly. Right, cool. Just not sure how long it will take. But we have a very, very talented team. They're working night and day to make it happen. And like I said, the critical thing to achieve for the revolution in spaceflight and for humanity to be a spacefaring civilization is to have a fully and rapidly reusable orbital rocket. There's not even been any orbital rocket that's been fully reusable ever, and this has always been the holy grail of rocketry. Many smart people, very smart people, have tried to do this before and have not succeeded. So, because it's such a hard problem.
What's your source of belief in situations like this? When the engineering problem is so difficult, there's a lot of experts, many of whom you admire, who have failed in the past.
Yes.
And A lot of people, a lot of experts, maybe journalists, all the kind of, the public in general have a lot of doubt about whether it's possible. And you yourself know that even if it's a non-null set, non-empty set of success, it's still unlikely or very difficult. Like, where do you go to, both personally, intellectually, as an engineer, as a team, like for source of strength needed to sort of persevere through this and to keep going with the project, take it to completion?
A source of strength. I that's really not how I think about things. I mean, for me, it's simply this is something that is important to get done, and we should just keep doing it, or die trying. And I don't need a source of strength.
So quitting is not even like
it's not in my nature.
Okay.
And I don't care about optimism or pessimism. Fuck that, we're gonna get it done.
Gonna get it done. Can you then zoom back in to specific problems with Starship or any engineering problems you work on? Can you try to introspect your particular biological neural network, your thinking process, and describe how you think through problems, through different engineering and design problems? Is there like a systematic process? You've spoken about first principles thinking, but is there kind of process to it?
Well, like saying like physics is a law and everything else is a recommendation. Mm-hmm. Like I've met a lot of people who can break the law, but I haven't met anyone who could break physics. So the first, for any kind of technology problem, you have to sort of just make sure you're not violating physics, and first principles analysis, I think, is something that can be applied to really any walk of life, anything really. It's really just saying, let's boil something down to the most fundamental principles, the things that we are most confident are true at a foundational level, and that sets your axiomatic base, and then you reason up from there, and then you cross-check your conclusion against the axiomatic truths. Some basics in physics would be like, are you violating conservation of energy or momentum or something like that? Then it's not going to work. So that's just to establish, is it possible? And then another good physics tool is thinking about things in the limit. If you take a particular thing and you scale it to a very large number or to a very small number, how do things change?
Both like like in number of things you manufacture, something like that, and then in time.
Yeah, like let's say take an example of like manufacturing, which I think is just a very underrated problem. And like I said, it's much harder to take an advanced technology product and bring it into volume manufacturing than it is to design it in the first place, by orders of magnitude. So let's say you're trying to figure out is why is this part or product expensive? Is it because of something fundamentally foolish that we're doing, or is it because our volume is too low? And so then you say, okay, well, what if our volume was 1 million units a year? Is it still expensive? That's what I mean by thinking about things in the limit. If it's still expensive at 1 million units a year, then volume is not the reason why your thing is expensive. There's something fundamental about the design.
And then you can focus on reducing the complexity or something like that in the design.
You could change the design to change the part to be something that is not fundamentally expensive. But like that's a common thing in rocketry because the unit volume is relatively low, and so a common excuse would be, well, it's expensive because our unit volume is low. And if we were in like automotive or something like that, or consumer electronics, then our costs would be lower. I'm like, okay, so let's say now you're making 1 million units a year. Is it still expensive? If the answer is yes, then economies of scale are not the issue.
Do you throw into manufacturing? Do you throw like supply chain, You talked about resources and materials and stuff like that. Do you throw that into the calculation of trying to reason from first principles, like how we're going to make the supply chain work here?
Yeah, yeah.
And then the cost of materials, things like that? Or is that too much?
Exactly. So, another like a good example, I think, of thinking about things in the limit is if you take any any product, any machine or whatever, like take a rocket or whatever, and say if you look at the raw materials in the rocket, so you're going to have like aluminum, steel, titanium, Inconel, specialty alloys, copper, and you say what's the weight of the constituent elements of each of these elements, and what is their raw material value, and that sets the asymptotic limit for how low the cost of the vehicle can be unless you change the materials. So. And then when you do that, call it like maybe the magic wand number or something like that. So that would be like if you had like just a pile of these raw materials here, and you could wave the magic wand and rearrange the atoms into the final shape. That would be the lowest possible cost that you could make this thing for, unless you change the materials. So then, and that is always almost always a very low number. So then, what's actually causing things to be expensive is how you put the atoms into the desired shape.
Yeah, actually, if you don't mind me taking a tiny tangent, I often talk to Jim Keller, who's somebody that worked with you as a friend.
Yeah, Jim was did great work at Tesla.
So I suppose he carries the flame of the same kind of thinking that